So hello, year three. I'm really sorry not to be with you in the classroom. I miss lecturing, and I guess you miss it too. So here I am in my home, talking to you in a little introduction to this year's laboratory testing course. I guess when you're an undergraduate student, you know, it's very difficult for you to know what is people's expertise. But I can assure you that this is my area of expertise, something I've been doing for 30-something years, and you wouldn't know, but I'm actually chair of the part of the International Society that's responsible for laboratory testing over the whole world. But that just means I'm getting old and near retirement. Anyway, so this is something I pretend I might know something about, I suppose. Last year I taught you site investigation, and the coursework was very well done, generally, and there were some excellent answers that sometimes just slightly disappointed me, because when I taught you site investigation, it's again an area of my expertise. I was trying to teach you ways for the future, and some of the answers looked very traditional, like current British industry practice. In no way was anybody penalised for that, because they were excellent answers and they were just what industry would do now. But I guess I was just a bit disappointed, because in my teaching, what I'm trying to do is to tell you how to do something better for the future. And what you have to know is that British technical industry is terrible in trying to adopt new methods and new ways of doing things. It's awful. You know, some of the techniques I'm going to be showing you are new techniques, but they're as old as you are a student. They've been around some time, and some of them I invented myself. But industry just won't adopt things, no matter how insane it is, no matter how much money they lose. Anyway, what can you do? But I hope, if you wouldn't mind, when you get to industry, try to persuade them that the methods that I'll show you in these lectures are the ones for the future, and we mustn't just sit on our laurels and use old techniques all the time. So if you ask people around the world what's Matthew Coop well known for, this is it. This is lab testing. So you will have to forgive me if I get a bit wrapped up in the details of what we do when I do the voiceover for the lecture. I'll try to cut to the important things. Students, of course, want to know what's going to be in the examination, and that will become obvious when we do the coursework. The coursework will highlight those aspects of the work that are most important. Okay, so with that's the last you'll see from me. I'll give you the voiceover, the lectures, and then we'll meet in live sessions. Okay, so see you soon. So what do we measure in mechanical tests? Well, really, in life, there are two forms of loading. Firstly, compression or consolidation. And we can do that isotropically in the triaxial apparatus. That's by increasing the cell pressure. That's isotropic loading. Or in the odometer, what we're applying is one-dimensional or K-naught loading. And the other form of loading, the basic form of loading, is shearing. In our shearing test, we really have some conflicting requirements of the tests, which are really unique to soil mechanics. No other scientist really has to solve this problem. Firstly, for strength, we need very large strains, you know, to reach critical states and things like that. And we need the minimum restraint in getting to that large strain, while hopefully the stresses and the strains remain uniform. At the other end of the scale, for the stiffness, we need to apply and measure some tiny stresses and strain changes that, again, I repeat, nobody else has to worry about. We are unique in soil mechanics. The triaxial apparatus is really the only apparatus that's able to do both of these. Before we get to the triaxial, I'll talk about an apparatus that's more familiar to you because we did it in year one, the direct shear test. So I won't labour this because you're all very familiar with it, I hope. That's a schematic diagram of the shear box test, where you've got sort of like a step loading here because of the design, with a normal stress sigma n and a normal shear stress tau. We like to pretend it's doing a perfect sort of shearing like this. Of course it's not, with horizontal and vertical displacements, and h0 is the initial height. Then we can calculate a shear strain. Remember, it's shear strain in the shear box. A horizontal strain is 0. The horizontal strain would be changing length. Now it's a shear strain, which is delta H divided by the initial height. And the vertical strain and the volumetric strain are the same. That's because the horizontal strain is 0. And those two, doesn't matter which one it is epsilon v, v for vertical or v for volumetric, and that's the change of height, delta v, divided by the initial height. I guess the only real advantage of a shear box is that the mode of shearing is plane strain. That means that, although I can show it on here that it's not changing length, so the horizontal strain is 0 that way, also into the picture, the sample is not changing its width. So it's plane strain. There's no strain into the picture. And that's similar to many engineering applications. Basically, any engineering application which is a very long structure will be plane strain. So most retaining walls are long, so the plane strain, embankments, cuttings, a dam, they would all be plane strain structures because they're long relative to their width or their height. And because they're long, you can assume that they're infinitely long. And if they're infinitely long, then of course there can be no strain along the length of the structure, hence plane strain. So if you like, this shear box could represent a slice out of a dam because there'd be no strain normal to my pointer. The problem with the triaxial is it's axisymmetric. You'll get the same stresses and the same strains, more or less, in the two horizontal directions. And there are no engineering structures really that are axisymmetric. Try to think of a few. There really aren't. Maybe underneath the tip of a circular pile, but just underneath the tip, nowhere else. Now, there are many disadvantages of our favorite shear box test. Firstly, you can't control the drainage. We did tests on dry samples in year 1, but of course, you know, if you have it saturated, there's no way to switch off a tap and stop the water going in and out. There's no control at all. Secondly, you may remember from year 1, all of the strains are localized, are occurring in the middle of the sample in this sort of lozenge that I've drawn here. And that means that when we calculate gamma and epsilon v, vertical strain or volumetric strain, they're very inaccurate because we're dividing by the whole sample height, whereas actually only this bit's doing something. And then you may remember that the other big disadvantage is we don't know the stress state. We only know 2 stresses, or one pair of stresses, a normal stress and a shear stress. That's 1 point. Now we can put an infinite number of more circles through 1 point. We assume that the correct small circle is the red one, giving us that failure envelope phi dash there. There's no reason why that has to be true. A more sophisticated problem with the shear box is that as you do the shearing, well, you can see that you might start when the shear stress is 0 with that normal stress being a principal stress. But because you're applying a shear stress, the principal stress must be rotating. Now that has an unfortunate effect. It will change the strength of the soil that you measure, especially if it's anisotropic, if it's got different strengths in different directions. So that's a problem. And then, of course, you'll remember that there's uncertainty about the calculation of the stresses. Which area do you use? So it does make a difference. This is a schematic of the shear box with, that's the initial area, A0. The area of contact with the soil might be this one here, AC, A current. And these are stress strain data from a real test, shear stress, shear strain, using the constant area, that would be A0, the red one, you get lower strengths. Using the soil only area, that's AC, that gives you higher strength. I don't believe either of them. I tend to use an average. But what you can see is that it makes a huge difference, particularly at the critical state down here. Not so important at the peak. The mode of shearing is also very important. We talked about plane strain, that's one mode of shearing. Axisymmetry, that's another. We can quantify the mode of shearing with what's called B, which is the intermediate principal stress minus the minor principal stress divided by the major principal stress minus the minor. Now you really have to investigate this in a hollow cylinder apparatus, which we'll talk about later, in fact, in the next little seminar. You could use also a true triaxial apparatus. Instead of having a cylindrical sample, you have a cubic sample with your major, minor, and intermediate principal stresses. If you do that, what you get is this. This is a friction angle plotted against B. Triaxial compression would be at B as 0. If you think about the definition here, triaxial extension would be at B of 1. Again, thinking about the definition here. Triaxial extension, by the way, is when you decrease sigma 1 while you maintain these two constant. So this stress actually then becomes the minor stress, not the major. That gives you B of 1. Well, if you look at typical data, like this one here for a typical sand, the friction angle goes up to plane strain and then reduces a bit. So this is what you measure in a triaxial, but a shear box test, plane strain, would give you a higher value. And that's good, really. Having higher phi dash in plane strain is good, because although we can get a phi dash that's very accurate in the triaxial, unlike the shear box, it will be conservative. In fact, in the design, what you probably should do is take your triaxial compression value and add a few degrees. Better that than relying on a shear box, which is just rubbish. And of course, as I said before, almost all engineering design is plane strain here, not triaxial compression, which is what we do. I'm going to spend a bit of time looking at a triaxial apparatus. Here's one. Everybody laughs at this old computer. Frankly, the triaxial test can last a month, so you can do the calculations on your telephone or your pocket calculator or something. You don't need a fancy computer. They just get stolen. So we use rubbish computers. The clever stuff is in here, and in the software, the algorithms are very sophisticated. This lot is £100,000 worth. That cost nothing. Remember, in a triaxial, the sample is in here in a latex membrane, and you're controlling inside the triaxial sample the pore pressure, which we denote U, the axial stress, sigma A, and the radial stress is provided by the water pressure in the chamber. That's sigma R. And remember, your effective stresses are simply the total stresses minus the pore pressure. So here's a schematic diagram of a triaxial sample with axial stress, and the two radial stresses, of course, the same. The advantages of a triaxial is that we can control the drainage. We can switch off a tap to make it undrained, not like a shear box. You know the complete stress state. We can calculate sigma R dash and sigma A dash from the pore pressures and total stresses. And therefore, we know where is the Mohr circle, and we know where is this friction angle. Disadvantage, as I've said a couple of times, is that it's axisymmetric, and soil parameters depend on the mode of loading. It's not the right one. We would prefer plane strain. This is really revision from year one, so we'll speed through this very, very quickly. Remember that your shear stresses don't mind whether they're effective or total, they're the same thing. Effective stresses are total minus pore pressure. Remember that on your triaxial, there is no shear stress on this boundary, Why? Because you're applying the pressure with water, and water doesn't transmit shear stress. So if there's no shear stress on that boundary, there's no shear stress on that boundary. So sigma A and sigma R are principal stresses. This should all be a revision. For drain tests, we're talking about drain tests here, your Mohr circles will therefore look like this. Total stresses in red, effective stresses in blue. They're exactly the same Mohr circles, they're just offset by the pore pressure. It doesn't matter where I measure the pore pressure, I could go from there to there. Any two similar points will give me the same value because the Mohr circles are identical, they're just offset. So that point and that point will have the same pore pressure. It's constant. It's the final Mohr circle at failure in effective stresses that defines failure. The total stresses are of no interest. And then if you remember your pole, well, your pole of your Mohr circle is there at sigma r dash. So the plane of failure will be that one, which translates to the same angle in reality in the sample. And that will be the plane on which you might get a well-defined failure plane forming. There's another plane of failure going to the failure envelope on this side, which is that one. Now for undrained testing, again, hopefully it's revision so we can go through it quite quickly. The total stresses just look like the same. The Mohr circle gets bigger as sigma A increases. The effective stresses, remember, they start off as a point. Initially, the axial and radial stresses are the same, and the Mohr circles increase in size. But here there's a catch. The pore pressure is changing. So the final pore pressure, UF, is different to U0. So the Mohr circles of effective stress are migrating. In this case, they're migrating towards the left. So sigma r dash is moving towards the left, and that's because the pore pressure has increased. You could have the other case where the pore pressures decrease and the Mohr circles would go off this way, getting bigger but going towards the right. The total stresses will always stay in the same place. Of course, if you want to represent the whole test, a Mohr circle is a bit useless because there are an infinite number of Mohr circles between the start of the test and the end of the test. So we do that with stress paths. And I hope you remember the definitions of P, which is the average stress, the mean normal total stress. Total, no dashes. So axial stress, 2 times the radial because there's 2 horizontal directions, all divided by 3. Engineers in industry love S, which is just axial plus radial over 2. They like that because that's the middle of the Mohr circle. Effective stresses, they're just dashes in here. So effective stresses, effective axial, effective radial, give you P dash, and same with S dash. In terms of Q, Q and Q dash are of course the same, and that's simply the deviator stress. The axial minus the radial stress doesn't matter whether it's total or effective, it's the same. And the same is true of T or T dash. It's half of Q. It's the radius of the Mohr circle, whereas Q is the diameter of the Mohr circle. So, for standard drain triaxial test, well, engineers love this because if they plot T against S or S dash, the total stress paths and the effective stress paths are parallel. They have a gradient of 1 and they're just offset by the pore pressure. It's drained, so the pore pressure is constant, so they remain parallel. It's more complicated in Q and P. The total and effective stress paths are again parallel, separated by the pore pressure U, which remains the same, but the gradient is 3, and you have to look at these equations, sorry, P and Q, to understand why the gradient is 3. Remember, sigma A is increasing, whereas sigma R is constant, so you can see that that's where the gradient of 3 comes from. So, T and S are loved by practicing engineers. They're easy, they represent the top of the Mohr circle, the gradient is 1, but they're not right. They're not invariants because in T and S you're forgetting one of the stresses. one of the horizontal or radial stresses has gone. They are not correct. Of course, if you did a well-designed test, you can see here with a normal triaxial test there's a problem. As you do the test, you're increasing the deviator stress, which is essentially increasing the shear stresses. But also you're increasing P dash. P dash is the normal stresses, which is a bit of a rubbish test to do. You know, any good physicist wouldn't do that. He or she would have a test where you increased only the shear stresses and you'd follow a vertical path and P dash would be constant. Now you can do that in a triaxial apparatus. If you look at the equation here, all you would have to do is to increase the axial stress while you decrease the radial stress at half the rate. You can do it. Nobody does it, which is a great shame. It's a more fundamental type of thing to do, separating the shear stresses and the normal stresses. You'll remember from year one that drain stress paths may go directly to a critical state on loose samples or at high stresses, and at dense samples or lower stresses you may go up to a peak and then back to the critical state. Of course, the usual test is this one here, at a gradient of 3 with the total radial stress constant and pore pressure constant. That's the gradient of 3. But as I said, with a computer-controlled apparatus, you can do anything. A particularly useful one is that constant P' test, which is pure shearing, no change of the normal stresses. But you can do anything you want. You can take these stress paths in any direction you want. In red, total stresses, in blue, effective stresses. And the offset is simply the pore pressure, and the offsets, the pore pressure is constant for each pair. Unfortunately, we don't typically take the advantage or the capability of the apparatus to do that type of thing. We could, for example, mimic the stress changes that we're expecting beneath our structure, but we tend not to do it. In undrained loading, remember that the soil is going to decide whether the stress path goes left or the stress path goes right. Over consolidated soils go that way, normally consolidated soils go that way. It's the soil that's deciding, not you. So if you change the total stress path direction, let's say just for this example, with that'd be like a normally consolidated clay with a stress path going left. If you change the total stress path by applying different stresses in your triaxial and it's undrained, it won't make any difference. The effective stress path will just be the same. All that will happen is you'll measure different pore pressures because you've chosen a different total stress path. The soil determines the effective stress path, not you. So here's the design of the triaxial apparatus. Firstly, remember that the radial stress is applied by water pressure in this chamber, water pressure in the chamber. That means that the sample has to be contained within a latex membrane to stop that water pressure going through into the sample. You can see the latex membrane here. That means that the sample will drain if it changes volume through this tube here, this drainage line, and we can simply switch off a tap there, and then we can control if it is drained or undrained. Because the sample's sealed, if we leave that tap open and it's drained, we can also change the pressure in here. We can change the pressure inside the sample. It's our choice what it is. This apparatus is a more sophisticated one, not typical of industry, but more typical in universities, which is a hydraulic one, and it's got a piston running up through here. The piston loads the sample from underneath, in fact, pushing it against a load cell, and you push the piston up with pressure in a chamber here. It's hydraulic. More typical is the type of thing that we would have talked about in year one, which is using a loading frame. And typically, one you might see in industry, the loading frame pushes a ram down to the top of the cell, pushing the sample from above. And that's rather less sophisticated, but unfortunately, that's what industry tends to use. So here's a rather complicated apparatus design. Let's go through it in step by step. Firstly, the transducers. The cell pressure transducer is just here. It's a commercial pressure transducer. The pore pressure transducer is here, connected through this line here to the pore pressure inside the sample. The axial stress, well, actually we don't measure the axial stress. What we do is we have a load cell here measuring the deviatoric force. That's the change of force from the isotropic state. So to calculate the deviator stress Q, you take the deviatoric force and divide by the sample area. Or the axial stress, you have to take the deviatoric stress plus the radial stress, the cell pressure. And the area you have to use in the calculation of the deviator stress is the current area of the sample, because the sample will be changing dimensions during the test. For the strains, for the axial strain, we have an LVDT here, which is measuring the axial displacement. As this piston moves up, it's moving this system up, pushing this displacement transducer up. Of course, we divide by the initial height of the sample to get the axial strain. The volume change of the sample is measured by measuring the water coming out of the sample and going into a volume gauge here, which measures the water coming out, or indeed going into the sample. Of course, you have to divide the volume change in cc's by the initial volume of the sample to get the volumetric strain, epsilon v. Typical apparatus have no measurement of the radial strain. Now that would be good, but it's not typical. So what we have to do to calculate shear strain, now shear strain would normally be 2/3 axial minus radial strain. We don't measure that one. So we have to take axial strain minus volumetric strain over 3. You work out the mathematics, it's the same thing. And also, because there is no radial strain, which would give us the current area very nicely, we have to calculate the current area for this calculation from the axial and volumetric strains, which we'll see in a minute. There are more advanced transducers, which we'll talk about in the next bit of lecture. Firstly, local axial strain transducers, which there's some shown here, some old-fashioned ones. Radial displacements are not shown. And there are mid-height pore pressure transducers not shown. We'll talk about that in a moment. But they would be on the sample here somewhere. This is the load cell that measures the deviatoric force, the change in force from the initial isotropic state. There's very specialized transducers coming from just soil mechanics, so they're expensive and unreliable. It's a load cell which is full of oil pressure, and I won't go into the design, but it makes them insensitive to changes in pressure. So if the cell pressure changes, the load cell reading doesn't change. It only changes when it presses down on the sample. I mentioned area corrections. Those are very important in soil mechanics and triaxial tests. So this is deviator stress against axial strain. This is data for London clay. And you can see the green line is the sort of raw data with no area correction, or just assuming, let's say, that the area is constant. The traditional area correction is what's called a right cylinder. You assume that the sample area just remains a cylinder, but a short fat cylinder instead of a tall thin cylinder. And you can calculate the new area like this. A naught, the initial area, 1 minus epsilon v, volumetric strain, divided by 1 minus epsilon a, axial strain. Of course, many samples, particularly one like this, which strain softens rapidly, they tend to develop a shear plane. Then I have to tell you that the calculation of the area to use to calculate these stresses gets more complicated, and I won't give you the equation. It's really too complicated for you. It's nasty. But then, of course, some samples will fail in a very complicated way like this, and then you can do nothing about it. There's no formula for that one. And the difference is significant, particularly at the larger strains down here at the critical state. which is what we saw in a shear box. We can measure the volume change on the sample by using a volume gauge device. This is the Imperial College type. The water comes out of the sample through a drainage line, pushes into a chamber, pushing a piston down, and that's registered on this displacement transducer. We can use the same device to apply pressure to the pore pressure by putting some pressure under here, transmitted through the piston and into the sample. The other way to get the volumetric strain is to measure the radial strain, but it's rarely done, in which case you would have the axial strain plus 2 times the radial strain as the volumetric strain. Measuring stresses and strains is common these days. Nobody does it manually anymore, even in industry. But what is less common is using control of tests by computer. Remember, I said the computer is a very cheap old thing, one that's come out of a rubbish skip. What is sophisticated are the control algorithms. They're very sophisticated, but we don't need fast computers because the tests are very slow. The test speed is controlled by the soil response, which is slow. So here we have our triaxial. The transducers send voltage out to the data logger. That sends a signal out to the computer. And that converts it into kilopascals. So this will be sending millivolts or something to the computer. The computer converts millivolts into kilopascals or millimeters and strains and stresses and things. That then decides how the test is running and what changes need to be made. It will send a command to a controller, and the controller will change things in the triaxial. So you know about the transducers, and I'm sure you've seen data loggers. The whole thing is called a feedback loop. What you don't know about are the controllers. So let's have a quick look at those. A very simple system like the Imperial College system is air-driven. So you need compressors to supply the air. There are 3 air pressure controllers, 1, 2, 3, one each for the axial stress, and the radial stress, and the pore pressure. You need air-water interfaces because, of course, the chamber has got water pressure in here, water pressure in here, and water pressure inside the sample. So you need air-water interfaces. Now, I already said that for the volume gauge, that provides an air-water interface. So air is going in the bottom, water pressure is coming out of the top and going into the sample. But the other 2, you need an air-water interface. So air pressure is coming in here, water pressure is coming out and going into the base of the sample. Likewise for the cell pressure. If we were to do a test where we just increased the axial pressure in this chamber and the soil were strain softening like the London clay we just saw, when we reached the peak, it would suddenly fail and the whole thing would move up suddenly as the sample collapsed. So we don't do that. What we do is we push water into this chamber at a controlled rate in terms of cc's per hour. And we do that with this device. It's a screw cylinder, a motorized screw cylinder, and it's similar to the one commercially made by a company called DS, which is this one. You have a motor and a gearbox driving a ball screw with a piston pushing water in that piston into the apparatus. Now that's happening at a controlled rate of cc's per hour, not a controlled pressure. Now the GDS system is a very clever one. It can be used to control rates of displacement, but it also can be used to control the pressure. The computer can move the motor up and down to give you a particular pressure in this cylinder. Finally, for this part of the lecture, I'll talk about philosophy of testing. There is an awful lot can go wrong with conducting and interpreting tests. We must never conduct and interpret tests unless we have a chosen and appropriate theoretical framework. We must know that theoretical framework, the one we want to use before we do the test. That's a problem because, of course, these days people do the lab testing long before they've decided what exactly they're designing, which is a major problem. The level of complexity of the tests must be appropriate to the theoretical framework and the design method, i.e., what we're designing. There's no point in throwing money away on really complicated tests for something that's very simple and not an important structure. You should never use a shopping list of tests. There's a temptation for young engineers to simply see what that was done on the last project and have the same tests. Why not? Well, no, that's not right. You have to decide, what quality of data do you really need and what do you need them for? Although I said you should be careful about doing appropriate tests to your design, the level of complexity should be appropriate. Large numbers of poor tests can be very detrimental when choosing a design value, and I'm going to show you a shocking example, which is from my own work. So this was my first project. I was barely 21 years old, so that's my only defense for such terrible design. I was designing these piles in a North Sea oil platform. Sorry, it's a gas platform, this one. And these piles are waiting to be driven through the legs of the structures here. Anyway, this is a design profile for undrained shear strength in the clay. Undrained shear strength was then called CU, now called SU. This is the depth. The problem is I plotted lots of data, some good quality like the undrained triaxials and some terrible quality like pocket penetrometer, which are, because I've not discriminated between the test data, it's all over the place. So my design profiles are these lines here, which are very conservative, simply because I'm plotting too much poor quality data. The reality would be somewhere up here. So large numbers of poor quality tests, cheap tests, meant that the design strength for the undrained shear strength was far too conservative. Must have cost hundreds of thousands, maybe millions of pounds, that mistake. So in summary, if they are to be well done, even our simple tests require quite a high level of operator sophistication and careful analysis. Be careful of cheap tests like a shear box test. They are of very little use, and better alternative tests exist. For example, a simple shear test, and I've not had time to cover that. Some simple and cheap tests have nothing much wrong with them. The odometer test is a fine test for one-dimensional compression, nothing wrong with that at all.